Hello friends. So in this video segment, let us solve a few problems on entropy, which is nothing but the average self-information. Now we know the general expression of entropy, which is given by H of S equals summation I equal to 1 to n pi log 1 by pi. Of course it is to base 2 because we are considering it in bits. So therefore the units of entropy H of S is bits per message symbol. And what is the expression for average source information rate RS? So RS is the symbols per second. Now if you assume that the source is emitting a fixed number of symbols per second, which is small rs, into entropy H of S will give us the average source information rate in terms of bits per second. Now using these two expressions, let us solve three problems. The first one, of course, is very simple, which you can see on your screen. You have all the three problems which are present on the screen. The first one is, of course, to find the entropy of the source. Three symbols S1, S2 and S3 with probabilities 1 by 2, 1 by 4 and 1 by 4. And the second problem is very important. And then we move on to the third problem, wherein we also come across a very important phenomenon of entropy, considering a binary source. So let us go through all these three problems very quickly. So the first problem states that consider a source S with symbols S1, S2 and S3 with probabilities 1 by 2, 1 by 4 and 1 by 4. So we need to find the self-information of each message and also find the entropy of the source S. So we have three symbols S1, S2 and S3 with these probabilities. So probability of S1 is 1 by 2, probability of occurrence of S2 is 1 by 4 and S3 is also 1 by 4. So self-information of S1, which is I1, so is nothing but log 2 base 2 1 by P1. So let this be P1, P2 and P3, the probabilities of the corresponding symbols S1, S2 and S3. So we have log 2 base 2, 1 by P1 is 1 by 2, so it is 1 by 2, which is log 2 to base 2, which is 1 bit. So by default, I have the operation of log in base 2 because I want the answer in bits. I want the self-information in bits. Next, I2 equals log 2 base 2 1 by P2, which is log 2 base 2 1 divided by 1 by 4, which is of course log 4 to base 2. So 4 can be written as 2 square, so log 2 square to base 2. So I get 2 into log 2 to base 2, which is 2 bits. So here I get this as 2 into log 2 to base 2. So log 2 to base 2 is of course 1, so I get 2 bits. And of course I3 is also equal to 2 bits because the probability is the same, which is 1 by 4. Now we need to find the entropy. So H of S, what is H of S? It is given by the expression summation I varying from 1 to n pi log 2 base 2. So we'll take it as log 2 base 2 1 by pi. So we have found out log 1 by pi, that is the self-information. So now I need to multiply the self-information with their probabilities. So basically it is equal to summation I equal to 1 to 3 because I have 3 symbols being emitted, pi I, so which is p1 I1 plus p2 I2 plus p3 I3. Okay, so therefore I get p1 is half into 1 plus p2 is 1 by 4 into I2 is 2 plus 1 by 4 into 2. So I get half plus 1 by 2, which is 1.5 bits per message symbol. So of course this was a very simple problem. So where we had to find the self-information as well as the entropy of a source emitting three symbols S1, S2, S3 with probabilities P1, P2 and P3. So now let's move on to the second problem. The second problem states that a code is composed of dots and dashes. We assume that a dash is 3 times as long as a dot and has a 1/3 the probability of occurrence. So we need to find the information in the dot and dash, and 2, we also need to find the entropy, and then we also need to find the average rate of information if the dot lasts for 10 milliseconds and this time is allowed between the symbols. So now what is being given? It is being given that a dash is 3 times as long as a dot and has 1/3 the probability of occurrence. So therefore, if I have a dot here, if a dot has of length 1, is of length 1, then a dash is of length 3. And the dash has 1/3 the probability of occurrence. So therefore, probability of dash is nothing but probability of dot divided by 3. So it has 1/3 the probability of occurrence. So what does this mean? So if I have 3 dots occurring, I would have 1 dash. So the probability of occurrence of a dash is 1/3 the probability of occurrence of a dot. So this is what has been given. So with this information, I need to find the self-information of a dot and a dash. I need to find the entropy, and also I need to find the average rate of information. Assuming that the dot is of length 10 milliseconds, then of course dash will be of length 3 into 10 milliseconds, and there is a gap of 10 milliseconds between any two symbols, between the occurrence of two symbols. Now we know that the sum of probabilities is always equal to 1, and there are 2 symbols which are occurring. One is a dot and the other one is dash. So therefore, probability of dot plus probability of dash is equal to 1. But we know that P dash is P dot by 3. So I have P dot plus probability of dash is nothing but probability of dot by 3, which is equal to 1. So I get 4 by 3 into P dot equals 1. So therefore probability of dot equals 3 by 4. So substituting 3 by 4 here, what is P of dash? Which is 1 minus 3 by 4. So I get probability of dash is 1 by 4. Alright, so now let's move on with the first one. So I need the self-information. So self-information of a dot is log to base 2 1 by probability of dot, which is 3 by 4. So which is log 4 by 3 to base 2. So what is log 4 by 3 to base 2? You have to use your calculators. 0.415 bits. So I'm writing the answers here. Of course you need to calculate and get the values. So now let us find the self-information of dash, which is log to base 2 1 divided by its probability, which is 1 by 4. So you have log to base 2 4, so which is 2 power 2. 4 can be written as 2 power 2 or 2 log 2 to base 2, so I get 2 bits. The first part of the problem states that I need to find the self-information of a dot and a dash, and we have done that. Now how do you find the entropy? So the entropy, which is nothing but H of S, is nothing but the self-information, which is I dot into probability of occurrence of dot, P dot, plus I dash into P dash, isn't it? So it's very simple. So multiply 0.15 with 3 by 4. So 0.415 into 3 by 4 plus 2, which is I dash into 1 by 4. Right? So I'll directly write the answer. So we get the value as 0.8113 bits per message symbol. So now what about the third part? Find the average rate of information if the dot is 10 milliseconds. So the duration of the dot is 10 milliseconds. So sometimes in the examination, this duration may vary. It can be 1 milliseconds, it can be 100 milliseconds. So here we'll do it for 10 milliseconds. So now we know that a dot is of duration 1 unit and a dash is 3 units. So therefore a dot duration is 10 milliseconds. And what about a dash? A dash is 3 into 10 milli, which is 30 milliseconds. And what about the occurrence? So we know that the probability of occurrence of a dash is 1/3 the probability of occurrence of dot, which essentially means that if I have 3 dots, I'll have 1 dash. Right? So that is what we obtained, isn't it? So we got the probability of a dot as 3 by 4 and probability of dash as 1 by 4. Right? Okay. So now this is 10 milli, this is 10 milli, this is 10 and this is 30 milliseconds. And what is being given? That there is a gap of 10 milliseconds between the occurrence of any two symbols. So between these two is 10, again I have 10, again I have 10. So you have 10, 20, 30, 40, 50, 60, 70, 80, 90. And then let's assume that I have a dot. So again I would have 10 milli. So the total duration would be 100 milliseconds. So you need to keep that in mind. So you have 3 symbols and there's a gap of 10 milli. So after a dash, the next symbol, either it may be a dot or a dash, will occur after 10 milliseconds. Alright, so therefore what is the symbol rate? So the symbol rate RS is nothing but 4 symbols. So I have 4 symbols in what is the duration? In 100 milliseconds. So essentially if I bring this on top, so this would be 4 divided by 100 into 10 power minus 3. Alright, so therefore you get 4 by 10 power minus 1, which is 4 into 10, which is 40 symbols per second. So you have 40 symbols per second. Now what is the information rate? The information rate RS is nothing but small rs, which is the symbol rate, which is 40 symbols per second into h of s, which is the entropy. So therefore RS is the symbol rate into the entropy, which is 40 into what is h of s? H of s we just calculated. It is 0.8113. So the units here is symbols per second. Here it is bits per symbol or message symbol. So I get the final value as 40 into 0.8113, which is 32.452 bits per second. So please make a note. If the symbol duration is 1 millisecond, suppose instead of 10 you have 1 millisecond. So now what happens? It is 1 millisecond there. So therefore, if a dot is 1 milli, so you have a dot and a dash. So each one is 1 milli, 1, 1, 1, and this is 3 milli. And in between again you have 1. So the total duration is 10 milliseconds. So instead of 100 here, you will get 10. In that case, RS would be 4 divided by 10 into 10 power minus 3, which would be 4 into 10 power minus 2, or it would be 400 symbols per second. So if the duration of a dot is 1 millisecond, if that is given in the examination, then RS would be 400 symbols per second, and therefore what is the information rate? It would be 400 into 0.8113, which would give me 324.52 bits per second. Right? So here it is 1 millisecond. So in the problem considered, the dot is 10 millisecond. So in the examination they can give 10 milli, 1 milli, or 100 milli, or 5 milli. So it may differ. So depending on the value given here, make sure that you calculate this correctly. So once this is calculated, then you will get the final symbol rate as well as the information rate. Right? So this is the second problem. So let's move on to the third problem, which is very interesting. So what does the third problem state? So the third problem states that a binary source is emitting independent sequences of zeros and ones with a probability p and 1 minus p respectively. So there is a binary source. So since the source is a binary source, it should emit 0 or 1. Now it's been given that the probability of the source emitting a 0 is p, and definitely probability of the source emitting a 1 would be 1 minus p, because probability of 0 being emitted plus probability of 1 being emitted is 1. So you have to remember that the sum of probabilities is always equal to 1. So if this is p, let's assume that this is p, then this would be 1 minus p. So the sum is 1. Alright, so now I need to plot the entropy of the source versus the probability. So now what do I get? So therefore, I have along the x-axis probability, and along the y-axis I would have entropy H of S. So remember that the probability always varies between 0 and 1. So let's take examples 0, 0.1, 0.2, 0.3, 0.4, 0.5, 0.6, 0.7, 0.8, 0.9 and 1. Okay, so now let us take these values. Let us assume that p of 0 is p, p of 1 is 1 minus p, right? Now let p of 0 be called as p1 and p of 1 as p2. So what is entropy? Entropy H of S is probability of the first symbol p1 into log 2 base to 1 by p1 plus p2 log 2 base to 1 by p2. Alright? Okay. So now let us consider different values. If I consider different values, I have p, I have 1 minus p. Observe, if p is 0.1, 1 minus p is 0.9. If p is 0.2, I get 0.8. 0.3, I get 0.7. 0.4, I get 0.6. 0.5, I get 0.5. And then what happens if this is 0.6? I get 0.4. If this is 0.7, I get 0.3. 0.8, I get 0.2. 0.9, I get 0.1. So these are the values I get, p and 1 minus p. So this is say p1 and this is say p2. So let's calculate the values. So for p equal to 0.1, what is H of S? It is p1 log 2 base to 1 by p1 plus p2 log 2 base to 1 by p2. So I get 0.1 log 2 base to 1 by 0.1 plus 0.9 log 2 base to 1 by 0.9. So make sure that you do the calculations correctly and get the values. So I'll write the answer, which is 0.469 bits per symbol. So I've calculated the values and I'm writing the values directly. Next, for p equal to 0.2, what is H of S? So I have 0.2 log 2 base 2 1 by 0.2 plus 0.8 log 2 base 2 1 by 0.8. So what do I get? I get the value as 0.722 bits per symbol. Next, P equal to 0.3. So H of S is 0.3 log to base 2 1 by 0.3 plus 0.7 log to base 2 1 by 0.7. So I get the value as 0.881 bits per symbol. So note that the entropy is increasing. Alright? Okay. So as P1 is increasing, so P is nothing but P1 here. Okay? So P1 is P, P2 is 1 minus P. So you find that the entropy is increasing. Next, P is 0.4. So H of S is 0.4 log to base 2 1 by 0.4 plus 0.6 log to base 2 1 by 0.6. So what do I get? I get it as 0.971 bits per symbol. If P is 0.5, what is H of S? It is 0.5 log to base 2 1 by 0.5 plus again 0.5 log to base 2 1 by 0.5. Alright, so I can actually write it as 2 into 0.5 log to base 2 1 by 0.5 at 1 bit per symbol. Now what happens when I put P equal to 0.6? I'll just do it for one. For the remaining you'll have to do it on your own. H of S is 0.6 log to base 2 1 by 0.6 plus this is 1 minus 0.6, 0.4 log to base 2 1 by 0.4. So where do I have this? I actually have this here, isn't it? You observe 0.4 log to base 2 1 by 0.4, 0.6 log to base 2 1 by 0.6. So what do I get? I get the same value, which is 0.971. So similarly, can you tell me for P equal to 0.7, what is H of S? I should get 0.7 log to base 2 1 by 0.7 plus this expression. So that would be 0.881 bits per symbol. Next, for P equal to 0.8, H of S will be equal to this, isn't it? 0.8 and 0.2 here. So you get 0.722 bits per symbol. And for P equal to 0.9, what is H of S? I get the same value, 0.469 bits per symbol. Now we did not calculate for P equal to 0. So what happens if P is equal to 0? The first expression of course is 0. 0. And what about this? This is 1. 1 log to base 2 1. Again you get it as 0 itself. Okay. So therefore we know that for P equal to 0, H of S equals 0. And for P equal to 1, H of S is also equal to 0 here. P equal to 0. P0 means P1 is 0, this is 0. So log to base 2. So this would be 1 here. 1 log to base 2, 1 is again 0. So we know that log 1 is 0 here. So again, if P1 is 1, this is going to be 0. So this again will be 0. So we have got all the values. So now let us plot. So along the y-axis, this is 1. So let this be 0.5. So the first value itself, we begin with 0 of course. So for P equal to 0.1, what is H of S? It is 0.469, just below 0.5. So you get 0.469, and the same value occurs again for P equal to 0.9. So for P equal to 0.9 again, I get these two values. Next, for P equal to 0.2, I get 0.722. So let me mark the values. So let this be 0.6, 0.7, 0.8, 0.9. Of course, this is not to scale. So 0.2 you get 0.722, just above this, above 0.7. So I get the value here, and again I get a value here. For 0.8 I get a value here. Next, for p equal to 0.3 I have 0.881. So very close to 0.9. So I have for 0.3 I get this value and I get this value. Next, for p equal to 0.4 it is 0.971. So very close to 1. So 0.4 and again for 0.6. And then again for p equal to 0.5 I get 1. So it's exactly equal to 1. So for 0.5 it's exactly equal to 1. So now let me join all these points. So I join these points. So what do you observe? You observe that the curve is absolutely symmetric about p equal to 0.5 for a binary source. That means if the probability of one of the symbols is p and the other one of course is 1 minus p, then the entropy would be the same if the probability of 0 is 1 minus p, right? So if the probability of 0 is 0.1 or 0.9, I get the same entropy. If the probability of 0 is 0.2 or 0.8, I get the same entropy. Similarly, if the probability of occurrence of 1 is 0.9 or 0.1, I get the same entropy because you find that the values are the same. Similarly, if the probability of 1 is 0.8 or 0.2, I get the same entropy. Right? So this is the plot of the entropy along the y-axis and the probability along the x-axis, and we get a curve like this. So we have seen a few problems, and in the next video segment we shall see a few more problems in this chapter. I hope you have found the lecture video informative and interesting. Make sure that you do keep solving more problems, and do not forget to like, share and subscribe and press the bell icon to get notifications of all the further uploads, and thanks for watching.